Okay, we're looking at the second partial derivatives given a contour map. In this case, we're looking at fxx, so second derivative of function f with respect to x twice, second time. So our contour map, we've seen this one, if you've seen my other videos, x squared e to the negative y. We take the first derivative, we take the second derivative with respect to x. I plug in this point here. And we notice that the second derivative with respect to x, or fxx, a partial derivative with respect to respect to x, is positive. So the first way you can look at it is the average rate of change. We saw from earlier that fx is positive between a and b. And here's that calculation there, just the average rate of change between a and b, where the change in function values is from 1.5 to 1. So therefore, the difference in z is 0.5. And the change in my x values, because I'm keeping y constant, is 0.7428 and minus 6065 is going to give us that number there. And then I'm going to look at the average rate of change between c and b. And same kind of thing. My change in z is still 0.5, right? Constant change in z values that are projected here. And from b to c, c to b is 0.8578 to 7428, gives me 4.34. And as you can see, if we have a constant change in z, because your contour maps are typically always going to have a constant change in between them, change in z. If I have a very big difference in between my change in x, which is the space in between a and b, so that is bigger than the space in between b and c. So if I have a big change in x, and I also have a small change in x, or smaller delta x, this number over here on the left is going to be smaller than this one here, just because I'm dividing by a bigger number. So just thinking about just fractions, a third is always going to be less than a half. And again, you have a constant change in z. You just want to look at the difference in between these points, and notice that the difference here is bigger than the difference in between here and here. So therefore, you could say that my fx, or the average rate of change, is increasing over these two intervals here. So therefore, we could say the partial of f with respect to x, or the first partial in the x direction, is increasing. And so therefore, we can say fxx is going to be positive in that scenario. Again, you just want to look at the change in the z values. The z values are increasing, and then you want to look at the difference in between each one of the points going in the positive x direction. I looked at it a different way. I plotted most of these points on the xy plane, where the z-axis is going to be my vertical axis, and my x-axis is going to be the horizontal one. And as you can see, the function is increasing. We already discussed that before. We said that fx is positive. It's not really clear, but it does look like there is some concave up going on here. So you can say that f is concave up, so therefore fxx is going to be positive in this case. Again, so you want to consider two different things. First thing you want to consider is the change in the z values. Is fx positive or negative? And then you want to look at the distance in between each one of those points. Is the distance in between those points getting bigger or smaller? And you want to put those two together and make your conclusion about is fxx positive or negative.